Assalamu alaikum, everyone. Welcome to this session on artificial intelligence. All right, so we'll be talking about neural networks as well as heuristics. We have already covered some topics. For example, we have talked about the types of AI. We've talked about two components of AI, which includes perception and reasoning. We have also talked about levels of intelligent behavior, which include reflex level and goal-seeking level and learning level. Then we saw a particular puzzle, and we used that as an example to illustrate how AI works. And then we saw some examples of automatic text generation. And we also covered semantic nets. This is when we try to extract information from either some written text or some spoken speech, and we try to recognize that, put them in words, and then try to see what are the links between them at a semantic level. Did we discuss something about a production system? Production system is an abstract problem-solving system, and most of these systems consist of these three states. These three components. One of them is the collection of states. The other one is the collection of moves. We take the system from one state to another, and finally the control system, which decides which move to make next. For example, if we are talking about the game of chess, then each chessboard position is a state of the game. And we can move from one state to another state by moving a piece on the board. So when a piece changes its position, it also changes the state of the whole entire system. And then what should be the next move, right? If we have a system, the reasoning system behind it, then it will decide which move to go ahead with next. And that's called the control system. So for example, this if we look at this puzzle as a production system, we can very easily see that this is a particular state in the system because these tiles are now at this point, they are randomly arranged. They are not in sequence. It's not like 1, 2, 3, 4, 5, 6, 7, 8. It is 1, 3, 5, 4, 2, 7, 8, 6. And we can change the state of the system by moving these tiles or sliding these tiles either to the left or to right, or we can slide them down or we can slide them up. So for each tile, there are some legitimate moves available to us, and the control system decides which has moves to be made next. So for example, this is a particular state in the system. We can change this state by moving the slides up and down or left or right. Now, in a particular stage, each slide has certain constraints on it, which means each state puts a certain constraint on these tiles, whether this tile can move or not, or if it can move, in what direction it can move, right? And when the state changes, these constraints change for all the tiles. For example, right now, for tile 3, there are no moves available. You cannot slide it left, right, up or down, right? In this position, it's fixed. But the tile 5 has one move available to it. We can slide it down. That's one option. And similarly, tile 2 has one option. We can slide it to right, and slide 6 can be, we can bring it up, the tile 6, right? Except for these 3 tiles, other tiles have no moves available to them. But when we do make a move, for example, when we push this tile 5 down, then tile 3 will have one option available to it, because there will be an empty space here, and 3 will now be free to move in this free space. Right? On the other hand, the number 2, tile number 2 will lose its freedom to move to right because now tile number 5 is already there, right? So now this new state has imposed new constraints on each tiles. Now, the task of the control system is to find out which move to make next. For example, in this case, it can either push 5 down, or it can push 2 to the right, or it can push 6 up. So it has got 3 choices. And which choice to make? This is the task of the control system. All right, so now today we will talk about something known as heuristics. So what happens in a heuristic? In order to understand that, we need to revise the concept of a search tree again. If you look at this search tree, you can see that it starts from a particular state. We might, for example, when we pick up the puzzle, it was in this state, 1, 3, 5, 4, 2, 7, 8, 6. And we want to arrange it in its goal state, which is shown over here, down here, right? So one of the techniques is to construct a search tree. Now the search tree is constructed by applying the 3 moves available at this state and then observing where that leads us to. For example, over here, we have only 3 choices, like I explained before. Either we can push 5 down, or we can push 2 to the right, or we can push 6 up. So if we push 5 down, we arrive at this new state, right? You see that number 5 has been pushed down, and now we have an empty space over here in its place where 5 used to be. And this was the second choice. The second choice was to push 2 to the right. Now you can see the 2 is on its right over here, and an empty space has been created where 2 was originally. And this is the third choice over here, in which we push 6 up, and which makes an empty space where 6 was before. So from the starting state, we had 3 choices, and we built that tree 1 layer at a time. So we built this first layer by executing all 3 choices that we had. Now for each of these 3 new states, we'll have certain choices. Over here, we have just one choice. Actually, we have 2 choices. We can either push 6 back, but if we do that, we'll go back to the original state. So we sort of discount that. The new state that is available to us is only one, which is when we push 8 to the right. Because in this state, there are only 2 choices available. Either 6 can come down or 8 can go to the right? All other tiles are fixed. So if we push 6 down, we'll actually go back to the starting state. So we are not focusing on that. We are focusing on what new moves are available to us. So the new move is when we move 8 to the right, and when we do that, we get to this new state, right? Similarly, we do this for the middle state over here, and we find there are 3 choices, and we construct all these 3 choices here. And finally, for this state, we had only 1 choice. Again, the 2 choices, but one was to go back. The new choice was just one, which is to come down over here, which is pushing 3 to the right. Now we have constructed the second layer of the search tree in this manner. And you can see that we can construct the 4th layer as well in the same manner. This is the next layer, you see, and then this is the next layer. And finally, in the bottom layer, we found that we have reached the goal state. So we don't need to go any layers down further from here because we have already reached the goal layer. Now, what you will observe in this is that while we were constructing the search tree, we were going level by level down, right? We complete 1 level and then we go 1 level down. So we move horizontally first and then vertically. It means it's in technical terms, it's called as constructing the search tree in a breadth-wise manner. So we cover the breadth first and then depth. Depth comes later, right? So no matter how wide the tree is, we construct the entire level breadth-wise first, right? So if there are three choices, there will be three states in the level below. If there were four choices, there will be four states in the level below. If there was just one choice, there will be one state in the level below. So the method of constructing this search tree in this manner is called that we go left to right in a horizontal manner first, and then we go down. There's an alternate available, which is called the depth first approach. In depth first approach, what we do is, let me stop share to clear these drawings. Sharing the screen again. Now, the in-depth first approach, what happens is that we, for going down, we select one of the sides also. Like we say, okay, we will go left, always left. Whenever we have choices available, we'll go left first. And in this manner, the way we construct is that we see, okay, what are the three choices available? So one of the choices available is to push 6 up. So we come down over here. And then we go further down, keep on going down. And when we encounter any options, we take the left option and continue our journey down. So this way of constructing the search tree is called as the depth first approach. When we go down as far as we can, and then when we reach to a point where we cannot go any further, we backtrack up and then choose the right path and continue in this way. For example, we come down over here, and over here we see that we cannot go any further because there are only two choices available over here. One is to push 1 up or push 3 to the right. We can continue with this. In this tree is breadth first, so that's why we stopped at this level. But in depth first level, we can continue going down until we reach the goal state or we reach some endpoint. Let me illustrate this concept with a simpler version of the same problem. I will construct this for you. You won't find it in real life, but let's suppose we have a similar problem in which instead of having 3 by 3 puzzle, we have a 2 by 2 puzzle, right? So, for example, the desired state is something like this: 1, 2, 3, and this is an empty space. I'm representing empty space by X so that you don't get confused over here. Or I can leave it empty also. If I leave it empty, it will be something like this. So now I have two choices available to me in this state, right? I can either push 2 down or 3 to the right. Okay. But this is the desired state. So I will start with a state which is not in the desired state. Okay, so let me draw this again. And let's suppose that what I encounter as my starting state is something like this: 2, 3, 1. Now, you know what's the desired state? I've just drew it, right? When all the tiles are in sequence. 1 is over here, 2 is over here, and 3 is down here in the bottom left, right? So the desired state, I'll just make desired state in green color up here. Let's say the desired state is this. 1, 2, and 3. Now, let me construct a search tree for this. So if this is the starting tree, I can go down like this, where I move 3 down, right? And these two tiles will remain the same. So what I've done is I pushed 3 down. This was one of the options. The other option is that I push 1 to right. In that case, I will come to this state where 2 is here, 3 is here, now 1 is over here, right? So this is one option available to me, and this is another option available to me. I'm just trying to construct a search tree. So if I go down further over here, now over here you can see that I have again 2 choices available to me. I can either push 3 up, or I can push 2 to the right. Now, if I push 3 up, I'll go back to this state, right? So I ignore that and I take the new option, which is to push 2 to the right, right? So I'll push 2 to right over here. 3 will remain in its place and 1 will remain in its place. When I'm in this state, I can either go back up, or I can enter a new state, which is to push 1 up, right? So I can, from here, I can go to this state, 1, 2, and 3. And you can very easily imagine that my next move will take me, it's actually, this is already the desired state. You can see that when I pushed 1 up, sorry, I did a mistake over here. This 3 is not here. So from this state, 3 was here, right? So I pushed 1 up and I got to this state. And from here, you can easily see that I can just move 3 to left and I'll come to the desired state. This is the desired state, right? No, this one over here. So you can see from here that this branch took me to the desired goal very quickly, because I was following this depth first approach. I could have done the breadth first approach, in which I would have constructed the next state over here as well, right? So the next state over here would be to bring 2 down, right? Because if I push 1 to the left, I'll go back to the original state. So the next state I have option is like this, right? I'm pushing 1 down over here. And after that, again, I have 2 choices. Either I can push 2 back to its original position, or I can bring 3 over here to get to the new state. And from here, I will go enter into another state, which is to push 1 up. And this will remain the same. And after that, I can push 2 to the right. And to continue in this direction, I will have to push 3 down, 1 and 2 will remain there in their place. And then finally, I will have to push 1 over here, 3 and 2 will remain in their place. And finally, I will push 2 up, and 1 and 3 will remain in place. And now you can see that this is now the desired state as well, right? So from the starting state, the search tree tells me that I have 2 options, right? Either I can go in this direction, or I can go in this direction, and both will take me to the destination state. But this one is a shorter route, and this one is a longer route, right? So the task of the control system is to find out which route should we take. And they have to make decision not by after constructing the entire tree. If we take this approach, it's called the brute force approach, which we do all the calculations and then find out which one of them was the shortest route to the destination. But that's not a very efficient way of solving problems, because it takes a lot of time in constructing all the states. Okay? So in order to make a shortcut, what we do is we employ some intelligent techniques, and one of them is called heuristics. And over here, we try to make a guess of which of these two options is a better option for us. Okay, so we are at this state right now, the current state. This is the state over here, and we want to decide whether we want to go down first, or do we want to take the other option, which means that do we want to push 3 down over here, or do we want to push 1 to the right? Now this is a choice we need to make. So if we employ a technique called heuristic, we will pick the choice that looks more promising, right? So although we don't know which one will eventually be the shorter, because until we construct all the states, we won't know for sure which one is shorter and which one is longer. But we can make a guess at this state, okay, which one looks better, which one looks promising. Although there's no guarantee, that's why it's called heuristic, because heuristics don't provide you with a guarantee, but they provide you with a good guess of which direction you should go in. But heuristics have this characteristic that most of the time they are correct, and they reduce the amount of time required to solve a problem. And humans do that in practice quite naturally, right? We always making our choices based on what looks good, right? We don't have any firm guarantees that this is the best choice, but we make an intelligent guess and say, this looks good. So we base our decision on our intuition, on our gut feelings. Okay, we should take this option because it looks good. We don't have a firm numerical answer of why that option looks good to us, but we do that in real life. And we call that as our intuition, as our feelings. But in computer science, computers can't rely on their intuition in that way. So what we do is we employ a technique called heuristics. Heuristics are a way of finding out which one is more promising, which direction is more promising. For example, over here, the heuristic that I can design is that I can find out which of these 2 moves that are available to me will take me closer to the desired state, right? And by closer, I mean, for example, I can just count how many tiles would be in their final position, or would be close to their final position after this move, or how many moves will it take to go from here to the final position. I can probably make a guess like this. For example, if I'm here and I make a move and I get to this state over here right now, I can evaluate this state of how good this looks, how promising this state looks, and compare it to the promise of this state over here. So let's call it this state 3 and this is state 2. I can compare state 2 with 3 to see which one looks more promising. So for example, I can evaluate this by calculating how far is each tile from its final position. Okay, for example, one should be up here. So it is 1 unit away. So I will just write 1 over here. 2 should be on this side. So it's also 1 unit away. And 3 should be on this side. So 3 is also 1 unit away. So there's a total of 3 units that I need to travel in order to go to the final destination. And over here, in this case, 2 has to move 1 place over here, and one has to move 2 places at least. It has to go here, so it's either I'll go up and left, or left and up. So it is 2 units away from its final position, and 3 has to come down here again. Now 3 again is 2 units away. Either it has to go left and down, or down and left to 2. So this state is 5 units away from the final destination. And let me also remind you that if you need to ask a question, you can please raise your hands if you need to ask a question, because I have muted your mics because there was continuously some background noise over there. So you can't use your mic at the moment. But if you have a question, you can simply raise your hands. There's an option available on Zoom in which you can do that, and that will let me know that whether you have a question or not. So our heuristic tells us that this is in some way closer to the final state than this one, right? So our heuristic will tell us that we should take this option rather than this. And then at each state, we can again apply the same heuristic to find out which is the best option to go to, right? So any questions about heuristics? G. Is it clear to everyone? What is heuristic? If it's clear, please give me a thumbs up. Okay, yes, thank you, excellent. Very good. Now the second topic, a lot of thumbs up, excellent. Okay, the second topic that I want to talk about today is something known as neural network. Now, neural network is a really exciting area of artificial intelligence, because thanks everyone who are typing in their responses, and those of you who are giving me thumbs up. Thank you very much for that response. Now, the second topic I want to talk about is a neural network. So what happens is that sometimes it's difficult to construct heuristics, because the difficulty in constructing heuristics is that they're not, there may be more than one heuristics, and some heuristics might be better than others. And designing which is the better heuristic is also a difficult task. For example, in case of a chess game, right? Devising heuristics is really difficult, right? How to give a numerical value to a new state. This could apply to many situations. For example, in case of self-driving cars, right? Devising heuristics would be very difficult again in that situation. So although this is a good technique, it's used in many applications, but it has its own limitations, right? We cannot apply the same technique in all the situations. So in order to tackle this type of situation, computer scientists have come up with another idea, which is based on this observation that humans are very good in doing certain things for which it's very difficult to write computer programs in a procedural manner. For example, recognizing faces. For humans, it's a very trivial task. Like even if it's a whole crowd of people, we can very easily find out where our friend is within the crowd, right? because we are very good at recognizing faces and saying, okay, this person is our friend or not. But it's very difficult to produce same kind of capability in AI programs. So what computer scientists did was like, okay, why not we mimic human brain in computation, and let's see what happens. So the idea was to see how brain works and then try to replicate that, not replicate that, but sort of simulate that in order to see whether these artificial brains can produce similar results. So they started off by looking at what is inside our brains. Inside a brain, as you know, are made up of specialized cells called neurons. Now, neurons have a specific shape and a specific function. And some of you might know that in a human brain, there are billions and billion, maybe 2 billion, I think, neurons, 2 billion cells, billion with the capital B, 2 billion, about 2 billion cells, and they are all connected to each other in the form of a network. And the total number of connections it runs into trillions. Okay, so if we try to draw a kind of a diagram for a neuron, which is the building block of a human brain or any animal's brain, is a cell, right? A cell is a biological cell. It has a body and some branches on two sides. So one is a long branch, it's called an axon, and there are the smaller ones all called as dendrites. Now these are medical terms. You don't need to really remember them very thoroughly, but just to make yourself familiar with these. Okay, so now we have, where was I? So this is the shape and structure of a neuron, right? It has a body, and it has some branches, small branches on one side and a long branch on the other side. Now this is also called as the output branch, and these are called as the input branches, right? Because they transmit electrical signals from one place to another, right? So it receives electrical signals on this side. They are connected to axons of other cells. These are axons coming from other cells, as you know, the billions and billions of them. So there might be many axons that connect to the short branches of this neuron, this one neuron, and you have signals coming in through all of these branches over here. So they get, these are the junctions which connect the axons with dendrites of another cell. So all these signals are sent to the body of this cell over here. And then this, depending on the combined strength of these signals, it either produces its own signal on the axon or it does not produce any signal. So it's kind of a binary system here, or you can say that the strength of the output depends on the combined strength of the inputs it's receiving. So this is the diagrammatic representation of a neuron. We can represent the same thing in a more kind of a mathematical model like this. Suppose this is the neuron, these are the inputs that are coming in, and this is the output. And there's a mathematical function that is happening over here. Let's say this is the mathematical function is plus, right? And it also has a threshold. Let's say the threshold is 5. Right? So if the inputs, suppose input 2 is coming from this side and input 1 is coming from this side, and input 3 is coming from this side. So this artificial neuron will just add up all these inputs. And the answer is obviously 6. Now 6 is greater than the threshold over here, 5. So it will produce an output. Let's say it always produces an output of 1. But if the if the inputs that are coming in, they are different. Let's suppose the inputs are 1, 2, and 1. Then the then the sum would be 4 over here, which is less than. Let me just erase this 4 over here. All right. All right, where I was. Again, sorry for this interruption. Okay, so the sum in this case is 4, which is less than 5. So there will be no output in this case, and the output will be, let's say, 0, right? So this is a very simple artificial neuron over here. It has 3 inputs and 1 output, and it can receive different values in the outputs. And what it does is just adds them all up and to see whether the sum is greater than some threshold or not. If the sum is equal or greater than the threshold, then the neuron fires, the artificial neuron fires and produces an output of 1. Otherwise, if the sum is less than the threshold, then there's no output or an output of 0. So can this small artificial neuron actually perform calculations that are similar to what humans do? The answer is surprisingly yes, and it's very effective. But what you need to do is you need to have lots of neurons, and you need to connect them and to make a network, right? For example, this is another neuron, and over here you have another neuron, and they all connect to the 4th neuron over here. So the output of this neuron would depend on the outputs of these neurons, whose output would depend on the outputs of other neurons. So we can have a network with many layers in it, right? And that's the difference between a neural network and a deep neural network. In a neural network, you have a small number of layers, like I've shown you on the diagram, but in a deep network, you have maybe several thousand layers. And interestingly, when you perform calculations like this, you can provide inputs, right? If you have, let's say, many layers. So in the first layer, you have a lot of inputs, a lot of neurons over here, and they provide their input to the next layers. These are all artificial neurons, and similarly, there are many layers. And finally, you have outputs on the final layer over here. So you can provide a lot of data to the input layer over here, and in the output layer, you'll have outputs from one of these, right? Not all of them, maybe one of them, maybe 2 of them. If they are, for example, just 2 outputs, we can, for example, add another layer over here and reduce them further to just 2 outputs. And we can connect them all together. So either this will, fire or this will fire, depending on what kind of data you get over here. And then we can train it, train this neural network to perform things. Now, what do I mean by training the neural network? For that, I'll have to go back a little bit more into the background and add a bit of more detail. So in an artificial neuron, what happens is that what the example that I gave you was very simple of just adding up the three inputs. But in a more sophisticated manner, what happens is that each input is actually multiplied by a certain weight. And that's where the whole secret lies in making neural networks effective. And the threshold remains the same. For example, the threshold is 5 over here. And output is either a 1 or a 0, depending on whether the result over here is greater than 5 or not. So let's say the weight 1 is equal to 3, and weight 2 is equal to 1.5, and weight 3 is equal to 2. So I can just write it like this. 3 and 2, so it's 1.5. 3, 1.5, and 2, and the threshold is 5. And let's suppose the input values that are coming in are 1, 2, and 1. So what this neuron will do is first multiply each input by its weight, and then perform the addition. So it will be 3 plus, I think it's 3 again, and plus this is 2. So it will be 8, and 8 is obviously greater than 5, so we will produce an output of 1. So in this, what is the advantage of having weights over here? The advantage is that you can let the network decide itself what are going to be the weights for each of these inputs. So let me draw a neural network. Let's suppose it has a lot of artificial neurons that are connected to each other in complex ways. And there's one more there. And finally, they are connected to one neuron, and there's an output. So let's suppose we have just 4 inputs. There will be obviously many more. So we have lots of inputs over here, but just one output, right? So the task of designing this neural network is to find out the weights for each of these links. And you can see that there are a lot of links over here, right? So for a human being, it's a difficult task to assign weights to all of these lines. So what happens is that we just randomly assign weights to all of them, right? And see what is the output. For example, there might be, all of them might be, let's say 1 million inputs over here. And these 1 million inputs corresponds to 1 million pixels in a picture. So I have a picture, or it has got 1 million pixels, and 1 million pixels go into this input layer. So input layer has got 1 million different inputs, but the output is only one. And I want to train this network to find out whether the picture I'm showing this is of a cat or not. So the answer is only yes or no, right? So what will happen in this case is that I'll show it a picture and the computer will randomly assign weights and it will generate either a yes or no, right? Suppose it produces, it's a picture of a cat, but it produces a no, right? So I will tell the computer that you have come up with the wrong decision. So in that case, the computer will change the weights again, using some techniques, obviously, with that we'll discuss it when we discuss AI in more detail, how the computer decides to make these changes. So it will make slight changes in each of these weights and then produce again the output. Once it makes the right decision, I will tell the computer that you have made the right decision. Then it will note down all the weights that it has assigned. So next time another picture of cat is shown to this neural network, it will try to use the same weights, but if it makes a wrong decision, it will make certain changes in those weights, and this cycle will continue. So what will happen is that the computer will try to remember which weights normally produce the right answer, and it will try to keep on refining those so that they become more and more accurate, and over a period of time it will become quite expert in recognizing the pictures of cat, although these all pictures are different. So this is how neural networks actually work in real life. Then you create a neural network and let the computer assign random weights, and then you train it. By training, it means that you show it a lot of pictures of cats until it starts distinguishing or recognizing the pictures of cat in an accurate way. So every time it makes a mistake, you tell the computer that you have made a mistake, and then the computer knows, okay, these are the wrong weights. We have to stay away from them. But whenever it makes the right choice, you tell the computer, and the computer decides, okay, these look better. Maybe some of them are still out of their range, and maybe so it decides which weights always perform good, okay, and which weights always perform bad, and it learns that, and eventually it finds out the right weights for all the links in the network. And then we say that it has now become trained in recognizing the pictures of cat. So we can then train these networks for various situations. For example, in case of a self-driving car, we can train it to observe how, whenever there is, for example, a left turn, what human drivers do, right? And then learn from that. So every time they make the right decisions, we tell them, and they memorize the weights or what kind of weights look more promising, and then they go in that direction, in the more promising direction, and refine their weights further and further. So the task of training a neural network is to show it a lot of sample inputs and provide it with feedback whether the decision it's making are right or wrong. And based on that feedback, the neural network learns and finds out which weights perform the best, give you the best output, and then eventually they become. So in real life, we have observed that if you show them enough samples and if you provide them with enough feedback, they eventually become as good as humans in recognizing, let's say, a picture of cats. Sometimes they may even exceed human capabilities. in that. But again, it's a very narrow domain. For one neural network that is trained on recognizing the pictures of cat will only do that, right? It will not be able to recognize picture of an elephant or so. So you'll have to train it again for that. But for specific purposes, these can be very useful. For example, in medicine, in detecting symptoms of a disease, right? Whether these symptoms signify presence of a particular disease, yes or no, right? So you can show this neural network a lot of symptoms, a lot of data from past that you have collected from the patients, right? All the patients that had these symptoms, they had this disease. And so that can help us in diagnosing the disease earlier so that it can be treated more effectively, things like that. So although they are very narrow domain applications, but we can train them in specific areas to make them more useful. So I think that was a short introduction on neural networks from my side. I will be happy to answer.
Sir, can you please re-explain the benefits of weight, of multiplying by weight?
So multiplying by weight, so when you adjust the weight, it will produce a different output, right? So you all you need to do is decide, try to distinguish between the right and the wrong output, right? So the advantage of having weights is that when you adjust the weights, eventually these networks become able to produce always the right answer for given inputs.
But sir, why is there a need to produce different weights? Why can't there be an equal weightage for each input? Always.
It's the reason is that so the if you look at a picture of a cat, right, and there will be many different variations. Like some of them might be black and white pictures, some might be color, the cats all look different. They're not exactly the same, but humans can recognize that this is a cat, not a dog. Although if you try to explain that in an if-then kind of situation, it's very difficult. How do you describe the difference between a cat and a dog in a series of statements? Okay, you might say, okay, dogs have the cats are smaller than dogs, but is that a fixed rule? And whether there might be some cats that are bigger, and is there like a sharp line? Okay, any animal larger than this size is a dog, and smaller than this size is a cat. Is that the
Yes,
only
yes.
criteria? Yes or no? So that's why it's difficult. So, but when you use weights, we don't know what weights actually produce the right answer. This is the mystery in a way. But human mind in a similar fashion. So what these neural networks are doing, they are just trying to mimic human brain. And if you ask the reason why a particular weight combination of weights produce the right answer, it's very difficult to explain that. So that's another challenge in AI, that the results it produces, they are difficult to explain why this particular set of weights have been used, right? So the theory behind there is a bit vague, but the results are quite accurate.
Sir, is it called black box learning?
Yes, it's a black box because we don't know what's happening inside the box and why is it happening, but it's just random hit and trial, and the computer then figures out, okay, this combination always produces the right results. So why this particular combination? Why not some other combination? This is the black box here. And thank you, everyone. That's the end of my session today.